Hello, welcome to the CSM Midterm 1 review session. We're doing a live recording of our review session instead of actually holding a review session because there are a lot of review sessions today and we didn't want to hold one on Sunday because we thought it would be too late. So my name is Albert. I'm going to be talking about the representation of variables in Java. All right, cool. So there are two types of variables, the first of which is a primitive, and the second of which are references to objects. And what that kind of means, I have this slide twice, but whatever. What that means is that you have to treat them kind of differently, or they're treated a little bit differently. So primitives include ints, floats, doubles, longs, shorts, bytes, chars, and booleans. References to objects are literally anything else. So for example, string, linked list stack, arrays, and literally anything else that you want. Those are all objects in Java. So the way I like to think about variables is to think of them as labels to a box. All right, so every variable holds some value in a box, and the thing in the box is what you get when you refer to that variable. So the reason why I talked about primitives and references to objects earlier is to let you all know that there's a little bit of difference in what is in the box, right? So for primitives, the thing in the box is the actual value of the primitive itself. So if you have int x equals 5, the thing in the box is actually the number 5. However, for references to objects, the thing in the box is not the object itself. Instead, it's a pointer to the object. So you don't put like a string inside a box. Your string goes somewhere else in your computer, and we don't care about where it is. The only thing that is in the box is the address of that string. So it's a pointer to where that string is living in memory. When we pass variables around, for example, to other functions, what we do is that we only copy what's in the box of the variable we're passing around. The original value of the box does not change. So in other words, what that means is that you can never change what is in the box for a variable when you pass it on to a function. However, you can change the values of an object that a reference variable is pointing to, and those changes can persist outside of your function. I'll go through a little demo with that really quickly. So for example, let's work with primitives first. So when we have a primitive, let's say we have int x equals 1, and then we kind of just go through. So let's see. In our main method, we have our int x, and the value in the box is a 1. Then we call change of x, right? So we open a new frame called change, and then toChange, that variable copies over what was in the box of x. So what was in the box of x? 1, right? So we copy that over. And now we're in the toChange method. And then after we go into the toChange method, we set toChange equals to 0. So notice what values changed, right? So up here, toChange was 1. Down here, toChange was 0. And that's the value that we change. However, once we return from that function, we will want to print out x, and that prints out 1. Because if you note here, even though we changed toChange, what happened to x? Nothing, right? Because we don't have access to the variable x within our local frame. So the x in the main frame doesn't get changed. All right, so yeah, we print out 1 because we copy the value of the box, or the value in the box of x into the function change, and then the value of x itself is not modified. All right, cool. So here's an example with a reference. Assume that we have a human object that has just a name, all right? All right, so the first thing that we do is we create our human object. So this right here is somewhere in memory, right? This is some location we don't care about. And the value of the box is this arrow right here, right? So what happens when we call change of that should be an al. Change of al, what happens is that we create a new frame, change, and then we have to pass in the variable, right? So we create a box called toChange. It's of type human, and when we copy over what's in the box of al. So what's in the box of al? It's this pointer right here. So we copy that over here, and it's still pointing to the same thing, all right? And now what we do is we say, okay, toChange.name is equal to Albert. So we say toChange, follow the pointer to the object, and then the name variable is changed to Albert. So see how this object itself has changed. But note that al and toChange have not changed at all in their pointers. Okay, so now that we finish executing change, we print out x.name and it prints out Albert. So once again, I pointed out earlier here that the value of al does not change. It's still a pointer to the same object. But what has changed is the object attributes itself. And since we're printing out al.name, we follow the pointer in al to the human object and then print out the name of that human object. Since we changed the attribute, that value of the human object, that change persists, and so when we print out x.name, we get Albert instead of al. Okay, cool. So that's just a brief overview of pointers, or I guess values in Java. Now we're going to do some practice, right? So this was taken from the CS61B midterm 1 spring of 2017. Okay, so what we have here is, let me make this bigger actually. Or actually, let me present this. View, present. All right, so what we have here is a previous midterm question. And as of right here, this line right here, that's where we're starting. So int x1 is 42 and int y1 is 12. So what goes in the box? X1 is initialized to 42, and since x1 is an int, the value that's in the box is the actual number itself, right? And same thing for y1. So they're both 12. And then we call swap of x1 and y1. So what happens here is we'll just go into this function call, and we gotta copy over the arguments, right? So we pass in x1 as x, and we pass in y1 as y. So when we pass these values into the function, what gets copied over? Well, since x1, or x is now x1 is passed in as x, we copy the value of what's in the box from x1 in our mainframe to the box in x, which is 42, and same thing for y. And then we just create a temp variable that's equal to y, which is, so what happens again is we create a new variable and copy over what's in the box of y. And then we set y is equal to x, and then x is equal to temp. Right, so this is a state of our function right now. Now what we want to do is we want to print out x. So in this case, what is x? Well, x is right here, right? And what's in the box of x? 12. So that's what we're going to print out. All right, cool. Now that function returns, so we trash this frame, and we go back here, right? And notice that x1 hasn't changed at all. So if you go backwards, oops. Yeah, if you go backwards, x1 and y1 have not changed at all. The only changes have happened in the swap frame. So when we return and we want to print out x1, what gets printed out? Well, whatever's in the box of x1, which is 42. And same thing with y1. So note that these have not changed yet. All right, cool. So next thing we do is we create two int arrays called x2 and y2. So here we go. Notice that arrays are objects, which is why that there's no value within the box, or the value of the box is just a pointer to this kind of array object over here. And same thing for y2. Now we want to call swap of y2, x2, and y2. So first of all, which swap do we call? This is an example of an overloaded method, and Java will figure out which method we call based off of the dynamic types or the static types that we pass into its function. In this case, we're passing in 2 int arrays, so it'll go to this swap and execute that. So let's open that frame, and notice again that what I'm doing here is I just copy the boxes, or I copy the value of what's in the box of x2 and of y2. And now I'm over here where I create a int array called temp and set that equal to y. So I copy what's ever in the box of y, which is a pointer to this array right here. And then we do the same swapping of variables, right? So when we say y equals x, what happens? We just copy the pointer. So now y is pointing to wherever x is pointing. And then when we say x is equal to temp, we do the same thing. And now we want to print out x of 0. So where's x? Right here, right? And what's x of 0? Well, we follow the pointer and we go to the 0th index, which is 4. So we print out 4. And once again, notice that everything we've done in this swap function has not changed what the values of x2 and y2 were in our main function frame. So when we return and we print out x2 of 0, it will print out 1. And when we print out y2 of 0, we will print out 4. Yep. And now we say x2 and y2 are equal to new ints of the same thing. And then we call swap of x2 of 0 and y2 of 0. So that's going to call this function up here because we're passing in just ints. And what happens is that we open a new frame. And we copy over what's in the box of x0, x2 of 0 into the value of x. So what's in the box of x2 of 0? It's this, right? Oh, oops, I pushed that. Yeah, so what's in the box of x2 of 0? It's the int primitive 1. So we copy that over into this box right here. And then same thing for y2 of 0. The value of that box is an int primitive of value 4. We just copy that over into this box. Okay, cool. So now we do the same thing that we did over here. And what we do is we create a new temp. We set y is equal to whatever x is. We set x is equal to whatever temp is. And then we print out x, which is 4. And once again, we haven't changed any of the values in the original function, right? So when we exit this function and we print out x2 of 0, it's still going to be 1. And when we print out y2 of 0, it's still going to be 4. Okay, cool. So that is like a walkthrough of the first question. Second question I'm going to do manually because that will make it a lot easier. Okay, cool. So how do I get rid of this? I guess it doesn't matter. Okay, so this is also a question from that same midterm. And what I'm going to be doing is I'm just going to be drawing out what happens so that I can kind of tell you like, oh, this is how I would think about it. And just a note here, if you look right here, there's 2 variables named the same name. For this example, let's just call this second one, let's call it ref instead of r. And that way this will compile. Okay, cool. So we can start, let's see. Let me make this a little bit bigger. Okay. All right, cool. So we create an int list 5000x. I'm going to abbreviate that with IL5. And here's our main. And now we have IL5x is equal to a new int list. So since we're creating an object, what goes in the box of x? It's going to be a pointer to where the object lives, right? So it's a pointer. And now I'm going to create my IL500 object. So IL5. And let's see, it has a IL5. Oh no, that was bad. It has an IL5 rest, which for this is going to be null. And then we also have a int primitive. I'm going to abbreviate that as prim. And that value is going to be 100. Okay. We're going to have an integer reference, I'm going to call that ref. That value is going to be what? So what is it, the difference between an integer and an int? Well, the integer is just a wrapper class for int. How do I get rid of this? Get out. Okay, cool. All right, so since it's a wrapper class for int, integers are actually objects. So what we have to do is we need a pointer, right? That was an ugly pointer. We need a pointer right here to an integer object. And what I'm gonna do is I'm just gonna say its int value is equal to, oh no, I don't have enough space. Okay, let's try that again, but this time with a bigger box. Okay, so this is the integer object, and it's gonna have an int val of 7. Awesome. And then another thing that we're gonna have is a static string slogan, right? So I'm just gonna call that, I'm just gonna write that up here. Slogan, it's a string, and it's going to be a pointer, right? Because these are all objects to this thing right here, and we're just gonna call it live. All right, so that's what happens as a result of this statement. And then when we create y, we kind of have to do the same thing, right? So il5 of y, and that should point to an il5 object, and it will have these values. So il5, oh no, I drew a B again. il5 of rest, and that value of rest is going to be x, right? So we copy whatever is in the box of x. Anyways, so now we're creating the il5, right? And we copy over what the value of x is. So what's the value of x? It's a pointer to that il5 object, so we copy that over. Now we have an int 9, so int prim, what's in the box? It's a 9. And then we have an integer ref, right? And we say, okay, we want to copy over x.reference. So what's x.reference? It's this, right? So we have a pointer to the same object because we're copying the pointer over, basically. And then since our slogan is static, we have to change the slogan. So now the slogan is eat. All right, so now that's what we've done. And here, since I can't write on Google Docs for some reason, I'm just going to write out what gets printed out over here. So what's y.primitive? So y.primitive is 9, so that's what gets printed out first. And then what's y.reference? So y.reference is this box right here, and since we're printing out that value, we want to follow this box to the integer object. And since the integer object's like toString method is just returning this, whatever its value is, it will print out 7. Okay, cool. Now what we want to do is we want to disinterbulate y. So now what we do is we will just create a new frame. So disinterbulate. That's going to be our frame. Get out of here. Okay. So now what that's going to take is an int list 500, so il5, and it's going to be called p. And what is that value? So what do we pass into disinterbulate? Well, we pass into y, or y into disinterbulate. So we copy what's ever in the box of y to wherever is to the box of p. So now we just copy the pointer because that's what's in the box of y. We say p.primitive is equal to 5,000. So now we have access to p, we follow the pointer to the object itself. The object itself has a primitive variable, and now we're changing that, right? So now the value of p.primitive is 5,000. Okay, awesome. And then we say p.reference is equal to new integer 1000. So once again, we follow the pointer of p to this object, and then we say, okay, its reference is going to be a new object, specifically a new integer. So now it points here. So here's our integer object. Int val is now equal to 1000. All right, cool, awesome. And then we say, okay, you know what? P is going to be a new int list. We don't like our current int list, so what we're going to do is we're going to get rid of this pointer right here, and we're just going to create a new int list 500 object right over here. All right, so IL5, it has an IL5 called rest, and that's going to be null. It's going to have a int primitive, and what is that going to be? That's going to have a value of 5, and it's going to have an integer reference. And since, once again, that's an object, we're going to have it point to an integer object. And now, since we pass in 10, that's like an int, right? What Java will do is it will actually automatically convert it to an integer because it knows that's the type right here that our constructor takes. So it'll create a new integer object. And it will have an int val of 9? Of 10. All right, and then once again, our slogan is a static variable. So since we just updated it, our slogan now must be relax. All right. Right, cool, and now P points to this object. All right, so now that we've done all of this, when we say we can exit this function, right, because we executed all of the code, and what that means is we get rid of everything or all the pointers and variables within this function, so we just get rid of this. Notice that the object itself doesn't get deleted immediately, but since there's no pointers to it, it will get garbage collected eventually. All right, and I'll just leave that there for now. Okay, so next thing we do is we've returned from here. Now we want to print out y.primitive and y.reference. So note here that y, the pointer of y hasn't changed, right? So y.primitive, what is that? That's 5,000 now. And then what's y.reference? Well, y.reference is whatever this value is, which is 1,000. Okay, cool. And now what we can then do is we call y.indoctrinate of 100. So here we go, indoctrinate. And then it's going to be taking in a int called b, and that's going to be 100. All right, cool. So now we say b is equal to 0. So now b is equal to 0. Let me erase that. And then since we said y.indoctrinate, we have access to this, right? So this refers to the y object itself right here. And when we say this dot rest dot primitive is equal to b, so we say this dot rest, so we follow that pointer to this int list 500 object, and then when we say the primitive is set equal to b, we set that value. We change this value equal to whatever b was. In this case was 0. So now we can exit this function call, and let me get rid of everything here. And now we have to print out x.primitive. So once again, x is this pointer, and that points to this int list 500 object, and we want the primitive value, which is 0. So it prints out 0. Okay, cool. And then what happens is now we say x.integrate new integer of 2000, right? So integrate is over here, and what are we passing in? We have access to integer v, and that box is right here. And since we're creating a new integer object, I'm going to create it right here, integer, and it's going to have an int val of 200. Okay, awesome. So now we say we did x.integrate. So now we say this.reference is equal to v. So what's this again? In this case, it's x. So whatever is x points to dot reference. So we're changing this value to be our new integer. So we can cross this out, get rid of it, change that pointer to be this pointer right here. All right, so now it points to 200. And then at integrate, we say v is equal to a new integer of 10, right? So we're using the new keyword, which means that, guess what? We're getting rid of this pointer, and then we actually just create a new integer again. So integer int val, and that value is going to be 10 this time. And that's what v points to. Okay, cool. So now we finished running what's in integrate, and we can destroy this frame. So once again, we just destroy all the variables in that frame. And since this integer object right here has no more pointers pointing to it, it will also get garbage collected eventually. All right. So the next thing we do is we print out x.reference. So what's x.reference? X is over here. We follow that pointer to the IL 500, and then we print out the reference, right? So the reference is pointing to this integer value right here, which is 200. So we print out 200. And then we print out endless500.slogan, which is up here. So this one's kind of testing like static, your understanding of the static keywords. So we print out the slogan, which is relax. All right, cool. And that's how you solve this problem. How do I pause this?
Stop it. You can stop.
All right, welcome to the static and dynamic types part of this CSM61B review session. So I'm going to be talking about static and dynamic types. As you can see, I already have some links here. So I presented this last semester, and there's a screencast link here, which is sort of live from last semester. So if you want to watch that, feel free to watch that. And on these slides, which we'll post, I'll also include a link to this video. Okay, so I'm going to do this whole thing about static and dynamic types in a bunch of steps. I think there are about 9 to 11 steps or so. And we're going to go over step by step and make sure we understand each part. So at any point, if you find yourself not understanding any step, it's time to sort of stop. Go back either in this video, the screencast video, or the slides itself, and make sure you understand each step before moving on to the next one. So before that, actually, static and dynamic types is something that I only truly understood not during midterm 1, but before my final when I took the class. And I think there are a lot of misconceptions and a lot of confusion about it. So I hope that this helps clear a lot of those up. And yeah, let me know if you have questions in the follow-ups of wherever this is posted. Okay, so initialization without casting. So first of all, we're going to talk about just initializing objects. When we say that, for instance, dog D equals new dog, what do we mean? Well, the way I like to think about it, and this whole video is essentially going to be a very large extended analogy. The way I like to think about it is doing this. So dog is on the left side is a static type, and this other dog on the right side is a dynamic type. So anything on the left is the static type, is how I like to remember it, and things on the right are the dynamic type. What does this mean exactly? So in my analogy, the way I like to think about it is a static type is essentially creating a box. So when the compiler hits this left keyword dog, it essentially creates a box, and this box is allowed to hold dogs. So it labels it dog, and then it creates a dog. So new dog means, create a new dog, and then it puts that dog inside this box. So now we should ask ourselves, well, is this okay? Of course, right? Because you have a box. It says that in this box, there can be dogs, because that's the label. And then we put a dog inside it. So everything so far, so good. Okay, now what about this case? Say that we have another class, bulldog, which extends the class dog. And what does it mean to extend a class? It just means that bulldog is a subclass of dog, or bulldog is a type of dog, or bulldog is a dog. So now again, I'm going to create a box. I'm going to label it dog. Then I'm going to create a new bulldog, and then I'm going to put the bulldog inside the box labeled dog. Is this okay? Again, sure, right? Because like I said, a bulldog is a dog. And the box says, I will let any dogs inside me. So this is not a problem because a bulldog is a dog. So this is fine. The compiler checks that what we're putting in the box is allowed to go in the box. Indeed, this is fine. And if you like a formal definition, essentially the compiler checks whether the dynamic type, in this case bulldog, is the same class as or a subclass of the static type, which in this case is dog. So the static type, once again, is the label. The dynamic type is what goes inside the actual object itself. Okay, what about this case? So we have now, say that bulldog extends the class dog, same thing, and bulldog D is equal to new dog. So let's think about this one. So now we have a box. We're going to label it saying bulldog. This box says, inside me there can be bulldogs. Then I create a dog, and I try to put it inside this box. Is this okay? So I'll take a second, pause, and think about it. Is this okay? Okay, so this is actually not okay because we are trying to put a generic dog inside a box which was specifically labeled bulldog. This is not going to be okay because the compiler is going to say it's possible that this dog is actually not a bulldog. It's possible that it's just a generic dog. It's possible that it's a poodle. It's possible that it's some other kind of dog. And so this is not something that the compiler is going to allow, and this is going to be a compiler error. And there are a few more. Say that cat and dog both extend animal. So animal is a superclass here, and cat and dog are the subclasses. And we have these 4 sort of examples. Dog D is new animal. So visualize this, right? We're going to create a box, label it dog, inside which we're going to try to put a generic animal. That's not going to be okay. Then we're going to create a box, label it animal, inside which we will try to put a dog. This is okay. Why is this okay? Because a dog is an animal, so this is fine. What about dog F equals new cat? Again, this doesn't make any sense because the box says I will let dogs in me, and then we try to put a cat in it. It's not going to work. What about cat C is equal to new animal? This case is essentially the same case as number 1, where we create a box, label it cat, and then we try to put a generic animal. It's not going to work. Okay. So if any of these are unclear, this is sort of a good time to pause and go back and watch this video again to make sure that you really understand what's going on here, or ask questions about it. Okay, moving on then. Yeah, what are your questions? Unfortunately, I can't take questions over the video, but feel free to comment them, and hopefully I or someone else will get to them. Okay, next let's talk about initialization and casting. So I'll motivate this and then we'll talk about it. Okay, so again, a little bit of a setup. We have dog D1 is new bulldog. So we have a box that has a bulldog inside it, and it's labeled dog, and this is D1. And then we have another one. This one is actually labeled bulldog and has a bulldog inside it. Now, again, remember the big idea? So the big idea, this is something that I haven't actually talked about. So the big idea is that after making these boxes, the compiler has no idea what's inside the boxes. What do I mean by that? Let me go back and talk about it. Or let's just talk about it right here. So as soon as the compiler sees this semicolon after this statement, the compiler does not know that inside truly is a bulldog, because essentially you can think of this box as being an opaque box. The compiler will create an object for you, put it in the box, and put a label outside the box. Now, as far as the compiler is concerned, the only thing the compiler sees is the label outside. The compiler has no idea what is actually inside the box. So the compiler only sees the static type. Remember this. This is a very important idea, and I'll say it again. The compiler does not see what's inside the box as soon as it hits the semicolon where the object is created and put inside its box. After that, the compiler only sees the label outside. Okay, so right, the compiler only sees the static type of objects. And so let's talk about this particular case, right? I'll leave this statement up here. The compiler only sees the static types of objects. Bulldog D3 is equal to D2. So what's going on here? First, I'm going to create a box, label it bulldog, and I'm going to call the box D3. Inside that, I'm going to try to sort of, the way you have to think about this is when we say equals D2, we're going to try to take the contents of D2 and empty them into this new box. Is this going to be okay? So the compiler sees, okay, new box is labeled bulldog, right? New box is labeled bulldog. It's called D3. And I'm going to look at this box. Again, the compiler does not know that this is inside. The compiler has no way of knowing this. But the compiler says, okay, sure, this box has a bulldog inside it because it can see the label. And it can just sort of take this box and empty its contents onto D3. That will be fine because everything will match up, right? This one is allowed to take in bulldogs. This one has a bulldog inside it. So the compiler says, fine. What about this case? So what's going on here now is we're going to create a box called D4, and we're going to label it bulldog. We're going to try to put the contents of D1 inside it. Once again, the compiler has no idea that this bulldog is inside the box. The compiler cannot see things inside the box once they've been put in the box. What's going to happen? So the compiler will create a box called D4 for a bulldog. And then it will see that this D1 box is labeled dog. So as far as the compiler is concerned, it asks itself, is it possible that in here there is a poodle or another kind of dog? And the answer is yes. So it's possible that this is not actually going to work, because it's possible that D1, the contents of D1, are actually not a bulldog. And so the compiler will not let this compile. The compiler says, D4 is labeled, wait for it, D4 is labeled bulldog, but D1 is labeled dog. So I cannot empty the contents of D1 inside D4. So this is a problem. And now you might think to yourself, well, this is a very stupid problem to have because clearly there is a bulldog inside, so this should be okay. And that's why we have something called casting, which I'm going to get into in just 1 second, but this is exactly what I'm trying to get at, right? We argue D1 is actually a bulldog. Compiler, believe me. And formally what's going on is that the static types of D4 and D1 are not the same, right? Remember, D1 static type is dog, D4 static type is bulldog, so the static types are not the same, but the dynamic type of D1, is a bulldog, can actually fit into the static type of D4. Right? The static type of D4 is bulldog. So this bulldog can actually fit in here. So we need to make the compiler believe us. And anytime you find yourself in a situation where you need to make the compiler believe you, that's where we do casting. So there we go. Believe me is casting. What we do is we say bulldog D4 is cast D1 to a bulldog. Okay. So in this case, as we can see, this will probably be okay, right? Because inside D1 there is actually a bulldog, so everyone should be happy. And indeed this will be fine, but essentially the way to read this line is this is the user, as in you, the programmer, telling the compiler, I know that the static type of D1 is dog, right? I know that the static type of D1 is dog. But trust me, there is a bulldog in D1. That's what this expression means. It means, trust me, I know the static type of D1 is something, but there is actually a bulldog in there. The compiler believes the user because it is possible that there is a bulldog in there. So how do we reason about this? I want to be very particular about this, which is that, remember, again, the compiler has no way of looking inside the box. Even with casting, even though I wrote this statement, the compiler cannot open the box, look inside, and confirm whether there is actually a bulldog or not. That's not what's going on here. What's going on here is the compiler asks itself. The programmer is telling me that there is a bulldog in here. Is it possible that there is a bulldog in here? So the answer is yes, right? In fact, it's also possible that there's a poodle in there. So the compiler would also be okay if you casted things to a poodle. What if you tried to cast things to an animal? What's going to happen now is the compiler is going to say there is no way that there is an animal inside D1. Why is that? Because if we had tried to put a generic animal inside D1, the compiler would not have allowed it in the past. So that means that the compiler trusts itself. The compiler says, okay, yeah, it's possible that I let a bulldog in there earlier. Again, the compiler does not open the box and look inside. The compiler just says, is it possible that I allowed this to happen? The answer is, yeah. So the compiler says, okay, fine, I'll believe you. There is a bulldog in there, and it'll let this whole thing compile. So what it's doing is it's for the purposes of this statement, it's changing the static type of D1 to be bulldog. For the purposes of this statement, the static type of D1 is still dog because the box is still labeled dog. Temporarily, we are changing its static type. Okay. Now, as you notice, you could be lying, right? Because right now we're telling the truth where, there is a bulldog in here. We tell the compiler there's a bulldog in here. But we could be lying. And so now we get into the whole thing about errors and exceptions. So let's talk about that. There are two kinds of lies. Let's see what they are. Okay. The first kind of lie is the one that's simply caught at compile time. So let's take a look at this. Now I create a box called C4. I label it cat. And then I tell the compiler, hey, compiler, trust me that inside D1 there's a cat. The compiler is going to just call your lie. It's going to say there's no way that there's a cat inside. Why is that? Because the compiler would never have allowed us to put a cat in there in the past. So if the compiler knows that there is no way there's a cat in there because the compiler itself would not have allowed it, it's a labeled dog. So imagine in the past I'd try to create a new cat object and put it inside this box. The compiler would have just said no right then. So the compiler trusts itself. The compiler trusts the things that it has allowed in the past. It says, okay, yeah, I've always been correct. The compiler says, I would never have allowed a cat in there. So this is a lie, and it's caught directly at compile time because the compiler can catch your lie. And this will, if you try to run this, it will say compiler error, incompatible types, dog cannot be converted to cat. There we go. So don't lie. And so essentially this is the compiler saying there's no way that D1 can hold a cat. I would never have allowed this to be true during initialization. Good. There's a second kind of lie, which is a little trickier, right? And let's take a look at what that is. So dog, real dog is new dog. So I'm going to create a box, call it real dog, label it dog, and inside that put a dog, a new dog, right? And then I'm going to say bulldog fail equals cast to bulldog real dog. So let's think about this. Again, I have this statement up here because this is extremely important and students tend to forget this very often. So don't forget this statement. The compiler only sees the static types of objects. What this means is the compiler cannot see what's inside. So again, imagine you're the compiler and you cannot see that inside here there is this dog. What is going to happen when you see this statement? You're going to create a box that says bulldog. It's going to label itself bulldog. And then you're going to tell the compiler, hey, compiler, believe me that inside this box that's labeled dog, there is actually a bulldog. Will the compiler believe you? Pause for a minute and think about it, and then I'll answer the question. So pause. Okay, the answer is that the compiler will actually believe you. And the reason is that, the compiler, all it does, again, it cannot open this box. So it cannot verify whether you're lying or not here. The compiler does not see this. The compiler simply says, okay, you're telling me that inside this real dog box, which is labeled dog, there is a bulldog. Compiler says, sure. Yeah, that's possible. I would have allowed that in the past, right? If I tried to put a bulldog in here in the past, the compiler would have let us do that. So the compiler has no way to catch this lie because the compiler cannot look inside. It says, fine. It is possible that real dog is actually a bulldog, so the compiler lets you compile. Now what happens during runtime? So let's talk about our extended analogy to the runtime. At the runtime, there are no boxes. There are only the objects themselves. And so what happens is that the runtime sees the dynamic types of objects, and the runtime says, you lied. Real dog isn't actually a bulldog, right? We said that real dog is a bulldog, like the dynamic type is bulldog, but we lied. And so this is going to be a class cast exception. It says dog cannot be cast to bulldog. It's going to be an exception. So this is going to be a runtime exception. And during runtime, your lie will be caught. So the crux of this whole thing, the main argument that I'm trying to make is that you can cast, but you cannot lie. Because if you lie, it'll either be caught at compile time or it'll be caught at runtime, but it will be caught. So there's no point in lying to the compiler by casting. You will get caught. And depending on what kind of a lie it is, if the compiler can catch it, it will. If it cannot, then it'll be caught at runtime, but it will be caught. Okay, so I'm going to pause here and then restart this. All right, so now let's move on to methods. So far all we've done is sort of initialization and casting in initialization. Now let's move on to methods. So let's take a look at what the requirements are to compile the code when you have method calls. Again, the compiler only sees the static types of objects. This is super important. It's still staying around here. And what else? This is just, I'm going to keep D1 around so we can use it as we need. D1 is a box labeled dog with a with a bulldog inside it. Okay, so now here's the big picture idea. The label, so the label class or the static class must be able to execute the method. Otherwise, there's going to be a compiler error. So let's take a look at what this means. Say that the dog class has a bark method, and the bulldog class inherits the bark method from the dog class. So, it doesn't have its own, but it just inherits it. And the bulldog class also has its own crawl method. So bulldogs can crawl and dogs can bark. And since bulldogs is 10 dog, they can also bark. Let's say we say d1.bark. What's going to happen? Well, again, the compiler only sees the static types of objects, so the compiler does not know that there's a bulldog inside. Remember that. Okay. d1.bark, the compiler says, oh yeah, d1 is a dog, and dogs have a bark method. So everything is fine. What about d1.crawl? So the compiler cannot see this, remember, again. The compiler says, oh, okay, d1 is a dog, but the dog class does not have a crawl method. The compiler says this is not okay, because the compiler does not know that inside truly is a bulldog. And this fails. This is a compiler error. The compiler only sees the static types of objects. See how that line is really important? Okay. Now, so this is about how to compile. It's fairly straightforward. The label or the static class just must be able to execute the method. Otherwise, there's going to be errors, compiler errors. Okay. Now, what methods should we actually run? So far we talked about whether or not we can compile, but what methods do we actually run when there are no arguments in the methods? We'll talk about what happens when there are arguments. Okay, so let's say that here's some code. We have a dog class that has a bark method, and it prints, I am a dog. There's a bulldog class that has a bark method, and you see how this bark method has the exact same signature, public void bark as dog. That means this method is being overridden. What overriding means is that you have an exact same method as your parent class. This bulldog class is extending dog. I'm sorry, it doesn't say that. It should be public class bulldog extends dog. And this bark method is being overridden. So it's a duplicate. It's a new definition of the bark method. And then we have public void crawl. And so this one prints bulldogs can crawl. Okay, and then we have a real dog, which is label dog and dog inside. And we have D1, which is label dog and bulldog inside. Okay, what about something like real dog.bark? First question, will it compile? The answer is already here. Indeed, real dog, which is, as far as the compiler is concerned, it cannot see this. It is a dog. And dogs do have a bark method, so everything is fine, all good. What does it print? Well, it'll print I'm a dog because remember, there are no boxes during runtime. So the boxes are all gone. We had called real dog.bark. Real dog is actually a dog. And so we will do I am a dog. Okay. Real dog.crawl. What happens now? So is this going to compile? No, because the compiler sees label dog. It asks, does the dog class have a crawl method? It doesn't, so it doesn't even compile. That's fine. What about something like this? So now we're saying, hey, compiler, trust me that real dog is actually a bulldog, and then we make it crawl. This is a lie, and lies always get caught. Where does this lie get caught? The compiler will say, indeed, it is possible that real dog is a bulldog, and so this lie will get caught during runtime. This is nothing but lie number 2. This will compile just fine, but it will not run. This is line number 2. If you need to look at that, you go back in the slides, and this is simply a class cast exception. Okay, what about d1.crawl? So again, it's labeled dog, and what's going to happen is that it's going to look inside the dog class for a crawl method. It's not going to find it, so this is not going to compile. What about bulldog d1 crawl? So now we're telling the compiler, trust me, there's a bulldog in here, and we tell the compiler, go look for a crawl method inside bulldog instead. The compiler says, okay, fine, I'll believe you, and it goes and finds the crawl method, and it compiles just fine. What about during runtime? What happens during runtime is the compiler sees that d1 was indeed a bulldog. Oh, sorry, the runtime sees that d1 was indeed a bulldog, and everything is fine, you didn't lie. So it runs that method, and it prints bulldogs can crawl, and everyone is happy, and all's good. All right, what about d1.bark? Now, the question that we're trying to get at is, does this get printed or does this get printed? So at d1.bark, the compiler sees, first of all, it sees the label dog. It says, does the dog class have a bark method? Yes, the dog class has a bark method. So the compiler says, okay, I see a bark method, I will let you compile. So the compiler lets you compile because of this method. The compiler has not even seen this method yet. The compiler lets you compile because of this method. But what actually runs? So to answer that question, let's talk about dynamic method selection. The compiler has now decided that no matter what, it will run a function that looks exactly like void bark, because the compiler compiled based on this, right? So this is the dynamic method selection part. And I'm going to say it again. The compiler has decided that no matter what, it will run a function that looks exactly like void bark. First of all, it's guaranteed that there is a function that looks exactly like void bark. And the reason it's guaranteed that is because this, right? It found it. So it can definitely run this if all else fails. Okay. Again, no matter what, the compiler has decided that no matter what, it will run a function that looks exactly like void bark. It doesn't care what comes outside of this box. Maybe inside this box, there's a baby bulldog or whatever, doesn't matter. The compiler will run a method that looks exactly like void bark. So during runtime, the compiler realizes that d1, not the compiler again, the runtime realizes that d1 is actually a bulldog. So it looks in the bulldog class for a method that looks exactly like void bark. Remember, the compiler decided that the method that will run will be void bark. You can think of the compiler as, sort of putting its foot down and saying a method that looks exactly like void bark must run. And now the runtime has to sort of obey the compiler's wishes. And so the runtime sees, okay, this is actually a bulldog. Let me look in the bulldog class for a method that looks exactly like void bark. It goes here and finds it. So it prints, I'm a bulldog. So far, pretty straightforward, but this part is going to get important really soon, this no matter what part, and this fact that it runs a method that looks exactly like something is going to get important in just a second. So far, this is fine. It says I'm a bulldog. What happens when you have arguments? This is where things start to get a little tricky. So far, we haven't had any function arguments. Let me again have the same two dogs, a real dog and a D1. D1 is like, it's a label dog, but it's actually a bulldog inside. Now, for arguments, compiler only looks in the static class. So what I mean by this is, if you call a method, let's say bark, that takes in a dog, then it will only look at the static class. It will not care about the dynamic class of the argument. And for arguments, the compiler tries to find the most specific method that takes in the static type of the argument. What I mean by that is, let's say that you have a method called bark, and the bark method takes in, there are two bark methods, let's say. One of them is bark and it takes in a dog, and one of them is bark and it takes in a bulldog. Now, let's go back here. You have, again, two bark methods. The first bark method takes in a dog. The second bark method takes in a bulldog. If you were to call the bark method on, by passing in real dog, it will choose the dog one. If you were to call the bark method with D1, it will also choose the dog one. But now let's say we had a real bulldog, right? A real bulldog with label bulldog and a real bulldog inside it. Then it would choose the bulldog method. So it tries to be as specific as it can, and it picks that method. Okay, let's take a look at this example. So this is exactly what I was going to talk about. We have a public class dog. There's a bark method, and it takes in a dog, D. And there's a public class bulldog, which extends dog. There's a bark method, it takes in a dog. And there's a bark method that takes in a bulldog. So this bark method prints I'm a dog, this one prints I am a bulldog, and this one prints I took a bulldog. Okay? Just as a review, these two methods are said to be overridden. And they're said to be overridden because the method signatures are exactly the same. Public, void, bark, dog. The name here is not important, so this could be D1, this could be D2, that would still be overriding. Public, void, bark, dog. Public, void, bark, dog. So once you have two methods that look exactly the same and are in different classes, where one class is subclass, the other class is superclass, this is called overriding. This is overloading because you have two methods with the same method name, right? So bark, and the same return type, void and void, but what they take in is different. So this one takes in a dog, this one takes in a bulldog. This is fine, this is allowed. It's called overloading. Okay. Now let's say we're going to do this. Real dog dot bark real dog. First, let's talk about the compiler. The compiler will choose bark dog to be the signature of the method it will run. Why is that? Because, so real dog, okay, real dog is here. Real dog's static class is dog. And that's all the compiler can see. So the compiler looks in this, it sees this bark method, and indeed this bark method works just fine for this, right? The compiler says, I will run bark dog to be the signature of the method, no matter what. The signature must be, in fact, it must be void bark dog. Okay. During runtime, we see real dog's dynamic type, right, is actually dog. So indeed, it actually just prints this method because it looks in the dog class. The runtime looks in the dog class, and it finds the method that looks exactly like void bark dog, and it will print this, I'm a dog. What about, don't worry about this note. This note is from last semester. What about cross dog dot bark real bulldog? So now we will look, okay, cross dog, the compiler will say, okay, the cross dog is a dog. So it will look in the dog class for a bark method. Yeah. It finds the bark method. The bark method takes in a dog, but that's fine. Remember, that's fine. Even though this is real bulldog, and the most specific thing to run would actually be this, right? Because the most specific thing to run is where it takes in a bulldog. But the compiler cannot see that method because the compiler, as far as the compiler is concerned, cross dog is a bulldog. Sorry, cross dog's static type is a dog, right? So cross dog static type is a dog. So the compiler, as far as it's concerned, it looks in the dog class. Okay? We look in the dog class, we find this method. Now the compiler decides that it will choose bark dog, or rather void bark dog, to be the method that it will run, no matter what. Okay? Again, the signature that the compiler has chosen is void bark dog. Now during runtime, there's a bunch of stuff that happens. Runtime realizes that cross dog's dynamic type is bulldog. Right? Cross dog's dynamic type is bulldog. Now, the compiler has decided that the method that will run will look like void bark dog. The runtime looks inside the bulldog class for a method with the signature bark dog, void bark dog, and it finds this. Again, notice that the best method to run would actually be this one, because this is the most specific. Bulldog is the argument. Real bulldog is the argument, and this would be the best method to run. But the one that we run is this one, because the compiler decided during compile time that the method that will run will have a signature exactly like void bark dog. And the reason we run this one and not this one is because during runtime, we realize that cross dog's dynamic type is a bulldog, and so first we check the bulldog class for a method that's called void bark dog, and we find it, so that's the one we run. This is so this is the tricky part here. Make sure you understand this. Make sure you understand this properly. If you don't, pause, go back, watch it again. But what's happening is the compiler, we compile because the compiler chose this method. The compiler says, oh yeah, this is the method we will run. It says void bark dog. It will choose this signature for you. The signature is the void, bark, and dog. But now during runtime, we realize that cross dog is actually a bulldog. Dynamic type is the bulldog. And so we look in here and we find the method with the exact same signature, void bark dog, and so we run this one. We never even look at this. So if the compiler has decided this is a signature that will run, we will never end up looking at this method. Okay? And once again, we don't care about the dynamic type of the arguments. We only look at the static type of the arguments. The dynamic type of the arguments don't matter at all whatsoever. Okay? What else? Oh yeah, so this whole thing is called dynamic method selection, where, during runtime, we look in the dynamic class for the method. But dynamic method selection only helps with overridden methods, not with overloaded methods. So these two methods were overloaded, these two are overridden. Dynamic method selection helps us pick between overridden methods, but not between overloaded methods. Weird things and what ifs. So imagine you have an ambiguity. What do I mean by that? You have a public class bulldog which extends dog, and you have a bark method. The first bark method can take in a dog and a bulldog. So in that order, dog, bulldog. The second bark method can take in a bulldog, dog in that order. The real question now is what method will run? Real bulldog dot bark, real bulldog, real bulldog. Both of these are actually, either one could run. They're both as specific as it gets. So remember what I said about specificity, right? We're going to pick the best method that we can. But which one is better here? They're both the same, right, in some sense, because real bulldog, the most specific thing a real bulldog can get is bulldog. So in either case, one of these two objects will have to sort of compromise and take a dog. What happens? The compiler sees two methods, both of which would work equally well. This will be a compiler error. And what about real bulldog dot bark, real dog, real bulldog? Which one gets picked now? So this one is actually okay, right? Because real dog, the most specific thing that it can take is dog, and the most specific thing that real bulldog can take is a bulldog, so the first one will get selected. And the compiler will decide that it will run a method that looks exactly like bark dog, comma, bulldog. Okay, if you have more what ifs, which I know many of you will, try them out. I don't know the answer to most of these what ifs. And with Java, there's a lot of what ifs that you can ask. We can keep doing this for, I don't know, hours and hours. But the best way to find out answers to more what ifs is to try them out. It's very easy, right? Just write a few lines of code and see what happens. It's also fun to do. So try it out. Okay, what about static methods? So static methods are not overridden. If you have two methods like this, public static void bark, public static void bark, I am a dog, I am a bulldog, you might think that they are overridden, right? Because they have the exact same signature, but they're not. Static methods are simply not overridden by definition. And these two methods, they're not overridden, they just exist. So you can call them like this. So if you do real dog dot bark, the one that gets called is dog dot bark because real dog is a dog. You can also call this method as dog, the class's name dot bark, with the name of the class. So this is fine too. Real bulldog dot bark, you can call it like this, and this is the method that will get called because it recognizes it's real bulldog. Or you can do bulldog dot bark again with the name of the class, and this is fine too. What happens when you do crossdog dot bark? When we do crossdog dot bark, it prints I am a dog because the compiler selects this method, right? The compiler says, okay, crossdogs, static type is a dog, and so the compiler selects this method to run, and then this is the method that runs. So for static methods, there's no dynamic method selection because they are not overridden. And remember, again, I said that dynamic method selection only helps with overridden methods, but these two methods are not overridden. So dynamic method selection will simply not help us. Okay, so we decide what to run during compile time by looking at the static class, and then we just run that method. No dynamic class stuff. Okay, we're almost coming to an end. I think there's step 10 and step 11. So everything sort of until now is extremely important. After this is a little bit of just some extra stuff. So let me quickly go over this. Factory methods. There are methods that can create an object and return it. So what is a factory method? A factory method is a method that creates an object and returns it. For instance, this, right? Public dog make new dog. So this method is a public method. It returns a dog, and it's called make new dog. It takes in no arguments. All it does is it returns a new dog. Return, creates a dog, and then returns it. Okay. let's take a look at this. So now we have, public class dog, it can bark, so dogs can bark, and it prints out dog. You have a public dog make new dog, and you have public bulldog make new bulldog. So the make new dog method makes a dog, the make new bulldog method makes a bulldog. And then you have public class bulldog extends dog, and bulldogs can bark and crawl, and so, barking it says bulldog, crawling it says bulldog crawl. Quick pop quiz, what methods are overloaded, what methods are overridden? Pause, answer the question, then I'll reveal it. Essentially, okay, pause now. Okay, essentially these two methods, so this bark method and this bark method, they are overridden, and there's no overloading happening. That's it. Okay, so let's take a look. Let's say we have this. Dog D is equal to real dog dot make new bulldog. What happens? So D will have a static type dog, and it will have a dynamic type bulldog. Because real dog dot make new bulldogs, this thing, right? This is the dynamic type, remember? And this will go here, and so its dynamic type will be bulldog. Because essentially you can think of this as dog D equals new bulldog, right? You can just imagine that this whole thing can be replaced by new bulldog, okay? What about this? Real dog dot make new bulldog. So, okay, now I'm nesting this together. Don't worry about this. Again, typo from before. I'm nesting it together. I'm saying real dog dot make new bulldog, whole thing together, dot crawl. What happens now? So real dog dot make new bulldog dot crawl, this whole thing, right? It's an underlying object. It doesn't have a variable to reference it by. This is just a sort of floating thing that we created. It's a floating bulldog. We created it. This thing will have static type bulldog and dynamic type bulldog. Why will its static type be bulldog? The reason its static type is bulldog is because of this return type. So this green thing means that its static type will be bulldog. This blue thing means that its dynamic type will be bulldog. If I had changed, so essentially this green thing means that its static type will be bulldog. This blue thing means that its dynamic type will be bulldog. If I change this to be dog, then what happens? You should try it out, okay? Now, let's look at another sort of thing, or let's just summarize this whole thing, which is just that the dynamic type for factory methods will be the class after the new keyword, which is essentially just this. After the new keyword, that'll be the dynamic type. The static type depends. The static type is either the type of the variable you're assigning the object to. So in this case, I am assigning the object to this variable, and so it will have static type dog. Or if you are not assigning it to anything, then its static type will just be the return type of the factory method. In this case, the return type of the factory method is bulldog. So that's what happens with factory methods. Okay? And finally, one last thing of casting. So far, we've only tried to make objects more specific by casting. What do I mean by more specific? We took a dog and we tried to cast it to bulldog, right? So that's making it more specific. A bulldog is more specialized than a generic dog in some sense. What about something like this, where we make it less specific? So we cast up is what we say, which is, we take a real bulldog, which has static and dynamic type bulldog, and we try to cast it to a dog, right? Is this okay? Remember, again, the dog class has a bark method, it prints I am a dog. The bulldog class has a bark method, it prints I am a bulldog. And the bulldog class has a crawl method that prints I can crawl. So the underlying part can never be an issue by itself. Because, what's going on here? We're never lying, right? If we cast up, we are never lying, because a real bulldog, of course, is a dog. So that's fine. But now the compiler is going to look in the dog class for the crawl method, right? Because remember, what this means is temporarily change the static type of this thing. And temporarily the static type of real bulldog becomes dog. And then we look in the dog class for the crawl method, and everything fails, right? It's not going to compile. But if we change it to bark, then the compiler will select this bark method. It'll say, oh yeah, sure, I can run this. And it'll be okay. And then during runtime, it will run bulldog's bark method, which it would have run without the cast anyway. This is because of dynamic method selection. Okay, so casting to a less specific class is a problem. only for static class method checking, and it makes no difference otherwise. All right. Okay, that was everything. If you have questions, again, feel free to post on the Piazza or wherever this is posted. Okay.
Hello everyone, welcome to the CSM61B Midterm 1 review. For this portion, I'm going to be talking about lists. So I'm going to be going over a review from everything from int lists to SLL lists, doubly linked lists, and A lists. I'll be talking about the characteristics of each one, and then finally we're going to end by doing some midterm final problems on these types of lists. So let's begin. So the very first list is the int list, and the int list is where it all began. The int list is the most primitive type of list in the sense that it's a naked data structure. What we mean by that is that within the int list, all of the nodes in the int list are themselves int lists. And so looking at the code for what an int list is, it has two fields. It has a first and it has a next, where first stores the int within a node, and the next points to the next node within it. And yeah, that's what an int list looks like. So once again, the properties of an int list is that it's naked. In order to actually get to an item within the int list, what we have to do is we either have to use recursion or we have to use iteration to get to that node. And because of this, this makes it actually really hard for the user to use. It's no fun for them because they can't just like directly index into it, or they can't call like a method like such as .getI to find whatever they need. And so therefore it makes it really hard and just not fun to use overall. So moving on to the singly linked list. So the singly linked list has this format in the sense that within the singly linked list, we have a node class. And within this node class, you can think of this node class as the int list class, where it has an item, it has a next field, and then it has a constructor. And if you'll notice in this definition too, one thing that we specified was that we specified this generic. So this generic T right here, what this does is this allows the SLL list to contain data of different types. And this is really important because previously, at least with the int list, the only thing that it could store was an int. And if we want a list with more usability, one of the things that we definitely need is to allow it to store data of multiple types. So what exactly is the SLL list and why do we need it? So the SLL list is like a modification to the int list in the sense that it's just a wrapper class around our int list. Looking at this diagram here, like this isn't what the final int list is going to be looking like, but this is what we have for now. So this LLL list, as you can see, it's just this box around this int list. And we'll see that by doing this, what we can do is that we can actually have a lot of different modifications and optimizations that allow the SLL list to be extremely user-friendly. So one of the optimizations that we can do is that we can abstract away all of the recursion and the iteration when we're actually moving through the SLL list. Specifically, we're going to put the recursion and the iteration within methods such as addFirst or .get so that the user can directly do what it wants to do. Furthermore, we're going to do two things such as add a size field and also a sentinel field within our SLL list so that we can directly access the first element in our list and we can keep track of the size of our list in constant time. So this is what the final form of the SLL list looked like. If we were to take everything that we did in the previous slide and do it to the SLL list, this is what we would get. And as you can see, the methods here with add first, get first, add last size, that's the method, that's all of the hard work abstracted away, and the users just need to call that in order to work with the SLL list. In terms of the sentinel node, you see that we've also added a sentinel node here. The sentinel node is very unique in the sense that we have it to avoid the null case, because in the case of a linked list, if the linked list is null, calling something like l.rest or l.next will cause the linked list, or will cause Java to throw an error. And so in order to not think about that case, we just always have a sentinel. One thing to note about the sentinel is that it's just a placeholder. So the value within the sentinel node doesn't matter. That's why we've indicated it with this question marks. And also you'll notice that the sentinel node doesn't actually matter for size. There are 4 nodes in total, but because one of them is a sentinel node, our size is only 3. And lastly, the size field. It's just when we have the size field, we can automatically track how many elements are in our SL list. And the way we actually work with the size is that we just update size whenever we add first, add last, remove first, and remove last. Okay, now on to the doubly linked list. So the doubly linked list you can think of as the final form of our linked list structure. And specifically for this doubly linked list, if you look at the implementation or the class definition, what you'll see is that there was a slight modification to our node. And in our node class now, instead of just having an item T and a node next, now we also have a previous, which points back to the previous node. So because each node now has a previous pointer, what we can do is that we're not just limited to moving forward, we can also move backwards. And because of this, it gives us a lot of freedom in the sense that we can move wherever we want. Additionally, with the doubly linked list, because of our ability to move backwards, we can actually have a back sentinel node. As you'll see here, we have a sent back field, which points to the very last sentinel node. And because now we have a .prev, if we want to find an item that's closer to the end, we can just use sent back, this back sentinel node, in order to get to where we want to go. There's also a different implementation for a doubly linked list. What you're seeing here is the implementation for the doubly linked list in which you have 2 sentinel nodes. But there's also a circular approach. In project 1B, you guys implemented the doubly linked list. Depending on which one you did, either this one or the previous one will look more familiar, but they all encapsulate, or they all cover the same idea. In this case, when you have the circular approach for a sentinel node, what's happening is just that you're having the previous of your sentinel node point to the very last item, and you're having the last item's next pointer pointing back to sentinel. And so it's, once again, it's the same idea, but just 2 different implementations. And whichever one makes more sense to you, you should use. Yeah, and this is just a recap of the doubly linked lists. So you'll see that it's actually really, really cool. After going from something like an int list, which is extremely primitive, and we have to use recursion to do whatever we want, to all the way to this doubly linked list where we have this wrapper class, we have all of these methods that we can use, we have size and our sentinel nodes, and we just have this amazing thing that's extremely user-friendly. And that's our end goal with the doubly linked list. So onto array lists. Everything that we talked about from int list to doubly linked list are related or can be thought of as belonging to the linked list family. Alternatively, there's another way to implement lists, and that's through arrays. So instead of having a linked list as your internal data structure, with an array list, the internal data structure is just an array. And specifically, the array that we're going to be using is a circular array. You guys also implemented this in project 1B, so this should be relatively familiar. With the circular linked list, or with the circular array, the idea is just that the idea is that you can move along both sides of the array. So you're not just limited to going from index 0 all the way to index 99. So the advantages of an A list is that because we're using an array as our internal data structure, we always have constant time access to whatever element we want. And this is just because of that syntax specified right here. In comparison to linked lists, this is actually really, really great because with linked lists, what we end up having to do is that if we wanted to find an element in the middle of a linked list, we would just have to move into one of the sentinel nodes and then either iterate or recurse to that position. And so in most cases, or in the worst case, it actually takes a linked list linear time to actually get an item from the list. So some potential issues though with the array list is that if you recall, one of the properties of an array is that it's not able to dynamically resize. What that means is that when your array becomes full, you just have to create a new array and copy elements over. And so we'll talk more about this in future lectures, but this is just a potential issue to think about, as the operation of copying everything over from your array to that new array when you're resizing could potentially take a lot of time. Okay, so that's it for the review part. For this part, we're gonna just jump into some questions and just go over like how to think about int lists and how to approach problems with int lists. For problem 1, we're gonna be going over int lists. In this problem today, what we're gonna be doing is that we're gonna be going over the main method, and we're going to be reading over each line and understanding exactly what it does. So even if you're feeling really comfortable with int lists and how they work, I would highly recommend for any of these problems where you're looking at the output of the code to just draw it out. And so in this case, how I like to start it out is that if we're working in the main method, we just specify the main field here. So in the very first line, what's happening is that A is assigned to a new int list 5 null. So we can draw it like this, which A is assigned to a new null. And then in the next line, we're doing system.out.println a.head. So the first field, or the head field of A, is going to be 5, and therefore we print out 5. In the next line, we're going to be calling B is equal to new int list 9 null. So therefore we say B is equal to a new int list 9 null. And then finally for the next line, we're saying int list C is equal to a new int list of 1. And specifically the tail points to another new int list 7, and the tail of that points to B. Afterwards, then we're going to call a.tail is equal to c.tail. And so this pointer now, or this field, is now going to point to whatever c.tail points to, which is this field right here. And just as a note, oftentimes one of the main confusion points is that when you have a pointer such like this, what this field is actually pointing to is it's pointing to the entire node. It's not pointing to any specific field within it, but rather the entire object. So that's just one thing to keep in mind when doing these problems. So after we've executed that line, the next line that we want to do now is we want to say a.tail.tail is equal to b. So in this case, a.tail.tail is equal to b. Well, a.tail.tail is already pointing to b, so we don't need to change anything for that line. Then to the next line, when we say b.tail is equal to c.tail, we look inside b, we change the tail field in b, and we say now it points to c.tail, which is just this node right here. And then in the next line, we're going to create another int list, and this int list is supposed to be called d, and it's going to have a head of 9001, and specifically the tail is going to be pointing to b.tail.tail. And so in this case, b.tail points to this, and b.tail.tail then points back to b. And so therefore 9001.tail will be pointing to b. Then finally, we're going to be printing out system.out.println d.tail.tail.head. So in order to look at what this prints out, let me just write it here, d.tail.tail d.tail.tail.head. Oh wait, sorry, there's one more tail. Exactly. So then, in order to just follow this, for the very first tail that we look at, the very first tail, we're going to follow it along, and we see that it points to B. Then we look at the tail of that, and the tail of that, we then follow it, and it points to this node right here. And then we follow that node, and we say dot tail. So we follow this node's tail to this node right here, and we print out its head. And so in this case, the head is just 9. So when we print out that, we get 9. Then in the next one, we call system.out.print.ln a.tail.head. What we do is we look at A, we follow its tail to this node, and then we print out its head, which is, in this case, 7. Afterwards, we do c.tail.tail is equal to c.tail. So for that method specifically, we're looking at C, and we're saying it's .tail is equal to C.tail. So specifically, this field right here is C.tail.tail, and what we're having it point to now is instead of having it point to that, we're having it point to C.tail, which is essentially it just pointing back to itself. To make this drawing a little more clear, I'll just erase this pointer. Oops. Exactly. So this is what the new diagram looks like after we've executed that line. And now for the final print statement, when we're trying to print out system.out.println a.tail.tail.tail.tail 1, 2, 3, 4 dot head. What we do when we follow this is that for the very first dot tail, we go A, we go to its tail, and then as you can see, for this node specifically, the tail of this node will always point back to itself. And so therefore, for the rest of these tails, what we're doing is just we're continuously circling around in this node. So at the end of the day, when we point out head, we're just printing out 7. And so now we finished with the problem, and this is just kind of an idea and approach to how to do it. So for problem number 2. So problem number 2 is related to doubly linked lists. This is more of the type of like harder problems that you're going to be seeing on the midterm. And specifically for this, what we want to do is that we want to fill in the code that they haven't provided for us yet, or to fill in the method definitions. One thing that I would like to say about these types of problems is that before starting it, it's a really, really good idea just to make sure that you know what's happening conceptually behind each of the methods that you're trying to do. And so with that, let's just go step by step and try and understand exactly what we need. So first off, when we're looking at this doubly linked list, within this doubly linked list class, we see that first it has a size, which is just 0. And then we have a sentinel node, which is a D node. And it specifically points to this D node, which is null, 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 null. Okay, cool. Then looking at its new methods, we see that we have public void add to front, insert, get node, and detach node. We'll talk about those, or we'll go over those a little later, but let's first actually look at the structure of class D node to try and understand exactly why our node has 4 fields to begin with. So looking at our static class D node, we see that in terms of our D node, which are the nodes that make up our doubly linked list class, we see that they have a key and a value, which are both strings. Then they have a prev and a next field, which are D nodes. And essentially, when you create a D node, you're assigning the key to K, value to V, and then prev to P and next to N. And so we see that in terms of the structure of this D node, It's very similar to just a normal node in a doubly linked list. It's just so that it happens to have two fields k and v, which are both strings. And then you have a previous and a next pointer. So this is the structure of the D node, and that's something that we always have to keep in mind over the course of this problem. So then actually going into the methods and trying to understand exactly what each method does. So in the problem statement, at least reading from what they've given us, it says that for space reasons, the code for insert front is hidden, but you can assume that it works properly. Okay, so in this case, let's understand exactly what insert front does. So for insert front, what we see is that insert front within this method, what we're doing is that we're passing in a D node to insert, and then all of the code is abstracted away. Well, looking at the method above, we see that add to front is actually the method that's calling insert front on the D node that we created. So whenever we add to front, we're passing in a string k, a string v. We're creating a new node with fields k, v, null, null. And then we're inserting it to the front of our list. So with that, let's actually go in and try to see what get node and what detach node has for us today. So in terms of get node, the method or the comments on what this method does is that it wants us to return a node containing k or null if the node doesn't exist. So in terms of this, it gives us absolutely nothing. We just simply have to work off of it and see what we need. So before coding, let's just think of like what could potentially happen or what do we need to consider when we're writing this. So there's just one case, and let's say like, so if the sentinel node at first, let's call this actually case 1, in which the sentinel node is just absolutely empty. There's nothing in the sentinel node, and so it's just filled with null fields. So that's one thing that we have to consider. Now, on the other hand, let's say case 2. So case 2 is the case in which our list isn't actually empty, and specifically that's going to look something like this, where our sentinel nodes are still going to be null, but our next is going to be pointing to some kv. It's pointing back. This is pointing to another kv, a different kv for that matter. So in this example that we see here, this is just another case where our list isn't actually empty. And so based off of these two cases, we can actually correctly reason about what we need to do when we need a get node. So after doing that, let's actually jump in and see how we can write the code for this. So the very first step, or the very first thing to note, is that in order to get node, in order to actually iterate through our doubly linked list, one of the things that we need to create is we need to create another node that points to sentinel. This is the get node method. The reason why we need this to begin with, or why it immediately comes to mind, is if we don't reassign the pointer to sentinel to a new variable, then essentially what's going to happen is we're going to be moving the sentinel node over and over and over whenever we call sentinel.next, because otherwise there's no way to iterate through it. So after we've copied the pointer to sentinel within n, then the other thing that we want to consider then is what exactly do we need to do? So actually wait, let me modify this just for a bit. Let's actually reassign it to sentinel.next. The reason why is that this will make it easier at the end when we want to know whether or not there exists a node with k. So for this method then, after we've reassigned, then we want to loop through and check to see if any node has this value k. So with that, let's just write a while loop. And within this while loop, our stopping condition is just simply if n is equal to null, right? Because if our node is equivalent to null, that means there's no more to go. And that if we haven't reached it yet, we'll never reach it. So while n does not equal null, we want to continue to loop through. But there's also another condition that we're missing, in the sense that it's not enough to just continue looping if we're not null, right? There's always something that we want to be checking for, and we just always want to check for if the node that we're currently at contains that key. So therefore, the second step is that we have an AND condition, and we say and n dot key dot equals k. And specifically, we want to see if it doesn't equal, because that's when we continue. And so therefore, if these conditions are satisfied, we'll continue to loop through, and we just say n is equal to n dot next. Once we finish the loop, we either have the value, or we either have the node, or we don't. And so therefore, all that we need to do is we just need to say return n. And this will solve all of our problems for us, because if we've reached all the way to the end of our list, n will be null, and so we haven't found it. If our list is empty, n is assigned to sentinel.next, and so therefore n will be null, and so return null anyways. And if we do find it, then n will be equal to that node, and then therefore we will return that node. So that's the solution for problem, or for the first part, for the get node. After finishing the get node method, we're going to be moving on to the detach node method. So for the detach node method, the method signature is that we're taking in a D node to detach that specifically we want to detach from our doubly linked list. And specifically, we're going to be returning nothing. So what that means is that we're going to be directly mutating that list. Whenever it comes to deleting nodes from a list, one of the things that you should automatically think of is changing pointers. And the reason why this is true is that, let's just take this example of a doubly linked list. So specifically in this case, right, you have a pointer from this node to the next, pointer from this node to the next, etc. If you want to delete, let's say, this middle node right here, this is the node that we want to delete, there's no true way of just like deleting this out from the middle of it. There's no method, and there's like just no way to do that. So instead of thinking about how to just delete that object in itself, what you want to be thinking about is how can I change the pointers such that this object essentially disappears. There's no pointers pointing to it. And in this case, what we want to do when we want to do something like this is we want to say, like, let's call this N1, N2, and N3. So in this case, if we want to change pointers to make this middle object disappear, one of the first things that we can say is that we can say something like N1.next is equal to N2.next, right? So what that does is it changes this pointer to this one. And then if we wanted to remove the previous pointer for this one, then all we have to do is we say N3.prev is equal to N2.prev, assuming that we knew, we had a reference to N3, N2, and N1. So this is the basic idea behind deleting, because what ends up happening here is that when we remove the references to this node, because as you can see here, there's nothing pointing to that node, right? The Java garbage collector will come along and just simply delete it after a while. And so therefore, what we're left with when we do this is we're left with this. And essentially, that's how our deletion is going to work. So using this logic, let's actually work with the toDetach method. So for the toDetach method, in all your methods, actually, you want to check just like in the case that you have some rogue arguments, such as like if it's null. So in this case, we just say if toDetach does not equal null, we will proceed. And so after we've checked that it's not null, then we just want to change the next pointer of our first node, or essentially in this case, let's see it like this. This is our to detach. This is the prev of to detach, and this is the next of to detach, right? So if to detach is not equal to null, the very first thing that we want to do is we just want to say to detach dot prev dot next is equal to detach dot next, right? And the reason why we can just automatically say this without checking for anything is even if to detaches next was null, then the pointer of dot next would just point to null. So this is perfectly fine. Then in the next condition, right? So after we've done this, the next thing that we want to do now is we want to change the next pointer back to prev. Well, what's interesting is that in this case, your to detach dot next could be null, right? And so therefore, if it's null, there's no way we can call like null dot prev. And so therefore for that, we just have to check if to detach dot next does not equal null. What we're going to do now is we're going to say to detach dot next dot prev is equal to detach dot prev. And so essentially what's happened here is that now we're changing this pointer right here. So instead of pointing back to detach, it now points to detach.prev. And so therefore, we've essentially done what we needed to do, and this middle node will be deleted. There is still one last thing though, and that last thing is just that whenever we want to detach, because we're keeping track of size within this doubly linked list, we just always want to have something like this, where we decrement size whenever we delete. And so with that, that's the correct implementation for this method. And so the general idea is just that always think through conceptually how you want to do the problem first, especially when it comes to these code fill-ins, before you actually write the code. And that's going to be really, really helpful like when it comes to the midterm.